All right. Welcome. This is the last part of the electrical series. And today I'm going to be talking to you about amplifiers, in particular audio amplifiers. And for that, I'm going to be covering some basic concepts and give you some practical applications for you to work on. So first, let's start by defining what an amplifier is. So if we think of a system where we have a signal, an input signal, and we want to have an output signal that to some degree is going to have some sort of amplification because let's say you're sensing um, uh, your heart, the heartbeat, or you're sensing some uh, distance from a sensor or some sort of like signal that is very small, let's say in the range of millivolts. Um, so you want to be able to amplify it. So that ratio between the output and the input is going to determine the gain of my system. And this gain can be seen in three different ways. So depending of what I'm looking at, I can either consider the voltage gain, which is going to be the ratio between the output voltage and the input voltage. Or I can look at the current gain, which is the same idea, but this time we're looking at the ratio between the currents. Or if we remember that the power is the multiplication between the voltage and the current, then we can also talk about power gain between the ratio of the powers. So just to give you a quick example. So let's consider a system where our input is going to be, for example, 1 milliamp at 10 millivolts. And this system is amplifying so that the output has a current of 10 milliamps and 1 volt. So if we look at the numbers, so first we will look at the ratio between the voltages. So for the ratio between the voltages, we will take the output voltage and divide it by the input voltage. I have changed the unit, so everything here is in volts. So we have 1 volt over 0.01 volt, that's 10 millivolts. So we see that the ratio is 100. So we're amplifying the voltage 100 times. If we repeat the process for the current, then we see that the current has been amplified 10 times. And if we take the product between the voltage and the current, then we see that the power that is being amplified in my system is in the order of 1,000. But as you can notice here, if we were to, this can scale up pretty quickly. So if we were to have, let's say, a current gain of 100, then this ratio for the power is going to go to 10,000, and if we keep increasing, this number can get really big. So normally this is correct. This is telling me like how much the amplification is, but normally people have used a different scale to quantify this gain. So that's where this unit that is called decibel is used, and this takes the numbers, takes the ratios, and transform them into a logarithm scale. So, and this is, if we were to look at the gain in decibels, which is uses the abbreviation dB, if we're looking at the ratio of amplitudes, then we take 10 times the logarithm base 10 of the ratio of the amplitude. However, if we are looking at the ratio of power, then it's not 20 times the log 10, it's only 10 times. So that's something to keep in mind as we look into measuring different gains, whether we're looking at the number, whether the numbers we're looking at are amplitude or power. So we need to keep that in mind to use the right equation. So if we look back at the example I gave you before, for example, we knew that the gain for the voltage was 100. So if now we take 20 times the log 10 of 100, that's going to give me 40 dB, because log 10 of 100, that's 2 times 20, that's 40 dB. The same now if we look at the current, log 10 of 10, that's 1 times 20, that's 20 dB. And now if we look at the power, now we need to remember that this is power, not amplitude. Therefore, we're using 10 instead of 20. So we have 10 log 10 of 1,000, that's 3 times 10 is 30 dB. So we see these numbers are much more compact, and they convey the same information. And whenever we look at amplifiers, whether for any project that you might be working on, or you're looking at some data sheets to understand like what's the range of amplification that your components can have, is typically expressed in dB. So it's very good to have an understanding of what they're talking. Decibels are also used for other applications, particularly they're using sound. So if you ever are doing anything sound related, usually those are expressed in dB to express differences or like amplification. So it has a range of applications. So if you're working in the lab and you're constructing a circuit for your project, you typically have like 3 major type of amplifiers. You have bipolar transistors, the ones that you're seeing on the upper right. They can come in like different like packages. This one I show you here, like a few of them can the shape of the chip can vary, but typically they have this like square shape with very long tips, or what do you call it? And they come in 2 different types, which I'm gonna mention in a minute. Then another type of amplifier is the MOSFETs, which you can see at the bottom right. It's usually their encapsulation is more like a square, and they typically come in these other kind of packages. And lastly, we have what is called an operational amplifier. They are more of a integrated circuit, and you can see it's like this kind of ship with like these legs coming out of both sides. The one I'm showing on the picture here in my slides is the LM741, which is a very common op amp that I'm going to demonstrate you later. It's also worth mentioning that although these three that I have here on my list are type of amplifier, they can also be used for other applications. So they are not exclusively for amplification, but they can also be used, for example, as switches if you want to turn on or off something. These have that behavior. Um, so they have a very wide range of application, and amplifiers is just one of them. So as I mentioned before, for bipolar transistors, there are two types, and the same applies for the MOSFETs. So you can see here is for transistor, the one on the left, we have two types, NPN and PNP. I will say what you need to keep in mind is that the symbol that is used, you see there is an arrow, where the NPN, the arrow is coming out, and for the PNP, the arrow is coming in, and also the emitter and the collector are flipped. So while both are commonly used can be used for the same applications, their configuration is going to be slightly different. Therefore, if you're ever looking at any type of circuit that you find online for that is relevant for your project, just keep that in mind that the symbols are slightly different. Therefore, whenever you're looking for the actual components to make your circuit, you have to keep in mind that for the symbol on the left, you will want a NPN transistor, but for the symbol on the right, you want to pick up like a PNP transistor. So they are different, and the same rule applies for MOSFETs. We can see the symbol is different from the transistor, but they also have an arrow to indicate their differences. So for the MOSFET, we have the one on the left is N channel, and for the one on the right is a P channel. And once again, drain and source are flipped just to indicate their configuration is gonna be different. So same rules applies here. Whenever you're looking at any circuits that might be used in MOSFETs, keep that in mind so you pick up the right one and connect it properly. As for the operation amplifier, the one I mentioned before, the 741 is probably one of the most commonly used one. Is a very basic op amp that can be used for a range of applications. So we see that it comes in this encapsulation of 8 pins. So the symbol of an op amp in a circuit is what is shown in letter A. We have two terminals for label with a plus and a minus. That's going to be my input. Then we have two sources for voltage. So we have positive voltage on the top, negative voltage in on the bottom, and these are going to be the voltage supplied by my power source. This power source can be the power supply in the lab bench, or it can be, for example, a 9-volt battery, or even can be your Arduino, depending on how much current you're going to be using. If you're trying to drive a motor that needs 1 amp to be able to work, most likely the Arduino might not be a good option since, if I remember correctly, the output of the pins is 500 milliamps max. So you might not be able to provide enough current through the Arduino, but depending on your application, you might or might not be able to use that as a viable power supply. And at the bottom, we see the diagram that shows the connections. So things to keep in mind as you work with this kind of integrated circuits. So we see in B where we have the 741, the encapsulation, the physical component. We see there is a dot. So you see like the grayish band on the left side and a dot right there. So the dot there is the same dot that is right next to the pin number 1 in the diagram at the bottom. So that's the way you like, if you ever look at the diagram, there is going to be always a dot that's going to indicate which one is your pin 1. And so that's how you orient, how do you identify which pin is what. So in this case, we see that pin number 2 and 3 are going to be my input, negative and positive. Then my power supply, at least the negative side, is going to be on pin number 4. And the positive side is going to be in pin number 7. And the output is going to be in pin number 6. Okay. So for the rest of the session, I'm gonna be mostly focusing on operational amps. I know there are multiple applications that can be done with transistors and MOSFETs, but for simplicity, I'm just gonna restrict myself to just show you a few examples with operational amplifiers. But this can be done with the others too. So one of the possible configurations that you can achieve with an op-amp is what is called an inverter. This inverter is going to take the signal, your input voltage, and with okay, let me take a step back. So the amplifier, what it's essentially doing is looking at the two terminals, negative and positive, and trying to make the difference between them 0. So what's going to happen whenever one of them becomes bigger than the other, let's say the negative terminal becomes larger than the positive terminal, then the difference between them is such that, okay, the negative is getting large, therefore that difference is amplified at the output such that I want that difference to become 0. So there is this through the resistor RF, there is this loop that is formed such that the current that's gonna go through that resistor is gonna be such that the voltage at the point X, where it says virtual earth summing point, I want that point to be the same as B1, which in this case is connected to ground, so it's 0. So I'm gonna be everything in my power to make that point 0. So if we were to resolve the equations, if you were to remember Ohm's law, that we know the voltage is equal the current times the resistance. So we know that this voltage input, assuming that is with respect to 0, we know that voltage it has to be the same that happens in the input resistor, because the point in X is equal to 0, and the stash once the difference of these two terminals becomes 0. So then the output is gonna adjust such that I can achieve that balance. And I'm gonna skip the math here, but if ever you I mean, if you have doubts or you want to know more, just let me know. But what you need to remember is that this setup, what it's gonna accomplish is that the output voltage is gonna be a scale version of the input based on the ratio between the RF resistance and Rin. However, we see that the minus sign here. Therefore, the signal is going to be inverted. That's where the name of this configuration is coming from. So, as you might guess, well, if there is an inverter configuration, there must be a non-inverter. And the non-inverter is slightly different. So here is the more what it looks like. Once again, I'm not gonna go into the detail of the math because for practical applications, what you really need to know is how to use it. So for this configuration, we see that now in the example before, the feedback loop was the feedback loop was coming back on the negative terminal, and my positive terminal was set to 0. Now we have changed the things a little bit. So my input is coming on the positive terminal, and my negative terminal now is having this loop with this resistor, and now the resistor that used to be connected to 0 on the positive terminal is put here now in the negative terminal. So if we were to resolve the equation for this configuration, we will find that the gain or the voltage output is going to be equal to the ratio between the sum of those resistors over R2 times the input voltage. So notice here that we have R2 plus RF over R2. So that's R2 over R2, that's 1, plus the ratio between them. So note that for this configuration, the minimum gain that you will be able to 1. You're always going to get something that is greater than 1. As opposed to of the other one, the inverter, here there is no restriction. You can either amplify or you can reduce the input. So you can go both ways. You can go up and down. For the non-inverter configuration, you cannot do that. So it's either no amplification in the case that RF is very small, or you have an amplification that is going to be at least 1. Okay. So that's for most of the content that I'm going to show you on the slides. So now we're going to be move on to the Tinkercad examples, and we're going to work on how to make these configurations. Let me share my screens. Okay, let's see. tutorial, where are you? Oh, there. Is that right? Yes. Okay. So, oh, actually, I'm just gonna copy the link. Okay, so I'm gonna put on the chat. Where is it? Okay, so I just sent you the link in the chat for the class, and I have created accounts for each of you. So just look at the your name, and there is some number that was added randomly. So I'm gonna ask you, once you have logged in, raise your hand so I know you guys are ready, so I can show you what you're gonna be doing. If you have any trouble like logging into Tinkercad, just let me know. All right, we have 2 people, 3 people, okay. All right, I think that was good. All right, so what I'm gonna ask you to do now, I have created a circuit. And what I want you to do is to recreate what I use. And I'm just gonna quickly walk you through it to show you what components I use. So now on your own, if you go to all the components on the right, we have the, you scroll down, and here we have the op amp. This is a 741 that I was mentioning before. For this one, we have we see the same setup that I showed earlier. If you like hover over the pins, it's gonna show you, oh, this is a negative input, this is a positive input, power and output, and the other positive power, negative power. What I'm showing here right now is the inverter configuration. So just a few things to mention. Every time you see a diagram, sometimes they might not mention the positive and negative power supplies. But if you want to be able to provide a signal that is both, goes all over the range for positive and negative, you want to be able to provide that. So what I've done here, given my limitations with Tinkercad, this is usually not a problem in a lab bench, in the power supplies that are in the lab. So if you look at the power supply that I have on my left, you see my negative is here in black, connected to the negative, and my positive is connected to the positive. And I have set up the voltage to be 10 volts, just to be on the safe side. Then I have this other one where, to be able to provide a negative voltage, I have made my positive connected to the same level of my negative on the other one. So this is going to be my ground. This is gonna be my ground level, so this is 0. And the negative, I have turned it into this other lane here that I'm gonna use as my negative voltage. So in this way, I set up my 0 in the middle, and I have 10 volts up and 10 volts down. So here, if you connect this correctly, we can see here, this is my function generator. I'm gonna be using a 100 hertz signal with 1 volt amplitude and no offset. And I just went for the triangular signal because I wanted to show you something particular, and I think that the triangle works pretty well. So again, negative is gonna go to my ground. My input is coming here to this lane. So here's my first resistor. I'm gonna set it up to 100 kilo ohms. So the resistor is coming to my negative terminal, and my other resistor is going also from the negative terminal into this point that is connected to the output. So this is the configuration that I showed you before on the slides, where the negative is connected to both the input through a resistor and to the output through another resistor, and the plus terminal is connected to ground. My power supplies, I connected the negative to my power supply here on the right, and the positive to the power supply on the left. So I'm just gonna turn it on. Unfortunately, here I have, if you have worked with the oscilloscopes in the lab, there is usually a sync option that allows you to sync a signal with respect to another channel, so you can see them with respect to each other. Unfortunately, that option is not available here, so I have no way to control the trigger. And even though this is supposed to be an inverter configuration, I can actually not see it through the tools that we have available. So that's kind of unfortunate. However, what we can see is that, oh wait, did it change? Yes, that does. Yeah, okay, so both resistors are 100, so 100 over 100, that's 1. So we can see that the amplification is 1. So they both have the same scale. So let's just change it a little bit. So if we change it to 10, we immediately see that now, although the signal remains identical, the scale has changed. Now it's 20 instead of 2, so that go with what we knew, that the amplification of this circuit will be 10 times. Okay, and something to keep in mind, the output of my my power supply only provides me with 10 volts. That's the maximum output, both positive and negative given my configuration. So what happens if I keep reducing the size of the resistance? Let's try it out. So let's go down to 5. Okay, it looks fine, right? I can still see the triangular signal. What if I change it to 4? Okay, now we start seeing something interesting. I'm actually going to change to 3. Okay, so as we keep decreasing the resistance here, we know that the amplification is given by the ratio between the resistors. So now the ratio is 100/3. That's 33.3. So that means that the amplification of my signal, which originally was 1 volt, so that volt now is amplified 33 times. Well, actually, that's a volt peak to peak. So that will be like half a volt times 33. That will be about 16. But we know that the maximum output of my power supply is 10. So we see this cropping saturation both at the top and the bottom. So that is something to keep in mind as you design amplifiers, that although in paper you have infinite power, like infinite amplification or anything you're doing, in practice you have a limitation. Either is the 5 volts from your Arduino, or the 9 volts from a battery, or whatever number you set up your power supply to. So if you don't amplify, if you amplify beyond the point where you're surpassing your power supply, then you run into this situation where you're cropping your signal. This in this case is depending on your application, it might not be terrible. I mean, well, this is well, with the sinusoid, it's very similar. If you're doing a square, the only difference with the square is just that it's gonna be cropped, and you actually don't see much a difference. But depending on your application, this might or might not be a concern. Okay. I don't know if any of you have any questions so far, or if you want time to like try to finish it, put it together on your own. No? Okay. So, well, it's unfortunate that I cannot show you the inversion part of this with this settings, but that is something to keep in mind. If you're amplifying audio, and you're running into this kind of situation with saturation, that's you're gonna hear it's gonna sound pretty bad. So that is something to keep in mind. And if you are, for example, trying to create an alarm of any kind with for I don't know, any reason that you might want. You might like you want to have an audible alert in your system. You can use this kind of configuration, especially with sound, that if you're inverting the signal, it doesn't really matter. It's the exact same signal, and you won't hear the difference in reality. However, the distortion here might make the sound worse, depending on what you're using as a speaker. You can also, if you build this, you can connect the output to a, there is here a, no, where are you? Oh, well, it is here somewhere. Oh, there it is. So if you were to connect the output here, you will be able to hear it, and that's, well, this is one type of piezoelectric speaker. Depending on what is available in the lab or what you're buying for your project, you might be using a different type of speaker, which might need a different setup. But one of the advantages of using an operational amplifier is that you can typically connect the output to this kind of speaker and expect it to work without much trouble. There is something called like impedance matching, and the output of the op amp is usually like high impedance, so that's usually not an issue. As opposed to if you're using a transistor amplifier, that might be something to design for, and you might want to look for for a circuit or or a design that is more appropriate for your speaker, as opposed to the op amp, which is normally more. It works better with most applications. Okay. So that's one example that I want to show you. Now, the other example is the non-inverter configuration. Again, unfortunately, I couldn't show you that the other one was an inverter because of how the oscilloscopes are set up here. Once again, the overall setup remained the same. I have changed the configuration of the resistance slightly. So in this case, we know that actually, let me go back and show you the presentation real quick. So if we remember, so we have this setup where we have the two resistors, one connected to ground, the other one connected to the output, and now the input is coming on the plus terminal. So now here, in the plus terminal, I have put a cable here to make it a little easier that is connected to my input. And the negative terminal, we have one resistor that is going to the ground, and the other resistor that is connected to the output. Everything else remains the same compared to the last example. So in this case, we have one resistor to be 40 kilo ohms, and the other one is 10. So is 40 over 10, that's a factor of 4, and we know is 1 plus the ratio, so that's 1 plus 4, so that's a ratio of 5. So let's take a look. All right, we see the scale on the left is 2 volts. The scale on the other side is 10 volts. So very good. That's a ratio of 5. So So now let's say we go 40. Again, this is, we talk that it's a ratio of 1 plus the ratios. In this case, the ratio is 1. So the amplification is 2. We can try to make this one smaller, and we will see that we somehow approach the gain of 1. Now it's like 1.25, so it's 1 1/4. No, sorry, it's 1 1/4. So yes, that's pretty small. And here we can see that that's 1 1/4. So we see some amplification, not much. Yeah, that's 80/40, and so on. So those are two typical configurations. We have the inverter and the non-inverter. Another thing to keep in mind, this is a setup where I'm using 2 power sources. As I mentioned before, you see, like, I have a power source on the left, a power source on the right, and so that's what allows me for the signal to go over 0 and below 0. If I were to connect the output to 0, and I'm actually just going to show you real quick what happens. So that will be that connected here. So now if you don't have the negative side, and you can actually see on the power source on the right that the current is 0, so there's no current flowing through that power supply, so I'm not using it. You can see that I have cropped the signal, and I only keeping the positive side. So this is something that can happen, especially if you are just working with an Arduino or just a battery, a 9-volt battery, where you only have a positive positive source, and you don't have 2 power source. So that is something to keep in mind. There are ways around it, and once again, different solutions are very application dependent. So it really comes down to what you're working on. So yeah, that's about all I have for today's. I don't know if you have any questions. I'm gonna stay here for maybe like 5 more minutes if any of you have questions, and I'll be happy to answer. Oh, that's a very good question. Usually maximums are set by the, let me actually show you, 11.7. All right, let me share my screen. Where is it? Okay. So whenever you're working with any kind of components, I usually, what I will highly suggest is to, in this case, let's say LM741 datasheet. So you want to look into the datasheet for any of the component that you're working on. In this case, let's look at the operation amplifier that I was just using. So there's going to be a short description of what it is, what is the typical application configuration. This is the one I was showing you. And what you want to find is here. This is what is really important and is relevant for your application. Let me zoom in a little bit. So in this case, we're looking at the specification. It says supply voltage for this circuit is you, depending on which model you're using in here, you have a maximum range of 22 volts. And there are some other specifications. For example, the input voltage that you can put into this is 15 volts. There is no output voltage limitation because the output is limited by the supply. So that's going to tell you, okay, I can put a signal of up to 15 volts, and the output, depending on my power supply, can be up to 22. So if you were to need an application where you need higher voltage than that, this might not be a good amplifier for that. So you might need to look into something different. A few other things that you might be concerned about is power dissipation. So you know more or less like how much power you're putting into your output. Let's say you're powering a speaker. A speaker, depending on the speaker, can be like 416 ohms. It's usually a very small amount. So if you know like you're putting 9 volts into it, or 10 volt maximum, that's gonna give you an idea of how much current you're putting into the speaker, and based on the current and the power that you're getting out of the amplifier, you can have a rough idea of your power dissipation. So, for example, this one it says can handle up to 500 milliwatts, and hopefully you stay under that. But that's also like just just because you're within the limits of the voltage, it doesn't mean that you're gonna be safe on the power dissipation. And so you need to be aware of how much how much voltage you're getting out of your amplifier, and how much current you're draining out of the amplifier towards your circuit or or sensor or whatever you have connected to it. So those, I will say, those are the two things you want to keep in mind. And again, this is gonna apply to transistors, to MOSFET, to even if you're working with Arduino. Arduino will have a data sheet where specification tells you, oh, this is how much current you can get out, this is how much voltage you can get out, and that's gonna tell you, okay, this is where I need to be, so I don't, burn my component. You don't want to fry it. So that's where you stay to be safe. I hope that answered your question. Awesome. Okay, I think if there, oh, no. All right, awesome. Okay, thank you for coming.